All right. Hey, Professor Lehman. My name is Nathan Reynolds. I'm in your ME 304 class, and this is video project number 2. So, the problem, we have to find the principal stresses and maximum shear stress at point H, which is right here. First thing we have to do to tackle this problem is we have to take a transverse cut at the point of interest, so right here, and then draw a free body diagram of the reaction of the cut and then solve for the reaction points or reaction forces. So first thing, draw it right here. Looks pretty good. All right, and then we have reactions in all the axes. So this is Y or RY. This is RZ. And this is RX. We also have moments about all these axes. So moment about Y, moment about X, and moment about Z. The reason we're finding the reactions is so we can use them to solve for the different load types. So the normal stress and shear stress due to either, and this problem is going to be axial, bending, and torsional loads. So, um, first thing we have to do, I guess we don't have to do this, but it makes it easier, is just identifying the different forces and where they are. Just going to make the cross products easier down the road. They're going to be in 3, I vector, j vector, k vector, I vector, j vector, and k. All right, so for the 50 kilonewton load, that one is straight up here in the y direction, so it doesn't go anywhere in x or z, so it's 0i, 0k, and then 6 meters up. In the diagram, it doesn't really look exactly like it's 6 meters, but that's the only dimension we're giving, so we're just going to go 6 meters. And then the force is 50 kilonewtons in the negative y direction, so it's 0, negative 50, 0. So now we have to do that for the other 3. So for 17 kilonewtons, we have 1.5 in the x, and then 6 in the y, 0 in the z, and it is again negative 17 y. 9 kilonewton force. This time it's going to be going in the positive x direction, but the position is 0 in the x, up 4 in the y, and then over 2.5 in the z. And it is a 9 kilonewton force, positive x direction. Now we have 13 kilonewton force, 0. J is going to be 4 meters in the J direction and 2.5 meters in the K direction, and is a negative 13 kilonewton force in the Y direction. All right, so now that we have all of our forces, we have the position vectors and the force vectors, we can solve pretty easily for the reaction in moments. Rx, Ry, Rz. But what just happened? Okay, that was weird. All right. All right. Rx. We only have one force in the positive direction, so the reaction force is going to be the negative, so negative Kn, so it can oppose that. Ry is going to be the summation of all the J forces, so negative 50, negative 17, negative 13. That adds up to negative 80, so our reaction force is going to be positive 80 kilonewtons. And then Z, we have no forces in the Z direction. So 0. The reason we didn't do a section for moment is because on the diagram there's no applied moment. If there was an applied moment, it would be there. But since there is none, we don't really have to account for it. So I just didn't do it. But the reaction moments, Mx, My, Mz, so we just solve for the moments. Mx, basically just statics. So moment about the x-axis. The only one of these that actually produces a moment about the x-axis is 13 kilonewtons. So it's going to be 13 kilonewtons times moment arm, which is 2.5 meters, which equals 32.5 kilonewtons per meter. And we can look at it, since the moment is going in the negative direction, the counterclockwise, or the positive direction, counterclockwise around the x-axis. The opposing moment, the reaction moment, is going to be going clockwise, so it's therefore going to be negative 32.5 kilonewtons per meter. Now we have to do the same for M and Y. 9 kilonewtons times the moment arm of 2.5 equals 22.5 kilonewtons per meter. And then we can look at it, see that it is producing a counterclockwise rotation, so the reaction is going to be clockwise, just negative. Thanks, man. And the moment about Z. Sorry, moment about Z. Where was I? Oh, 17 kilonewtons is the only one that produces a moment about Z. So 17 kilonewtons times moment arm 1.5 equals 25.5 kilonewtons per meter. And this time it's actually clockwise, so the reaction is going to be counterclockwise. So it stays positive. So now that we have all of our reactions, we can use these to determine the normal stress and shear stress. due to all of them and then superposition, we can add them up together. And that will give us the total normal and shear stress at H. I'm actually going to there we go. Makes it a little bit better. So first, we're gonna do the ones that produce normal stress. Start with Ry. Ry is going straight down towards H. Oh, I never drew this. H is right here. It's just on the z-axis. So this 50 kilonewtons worth of force is going to produce axial load, and it's going to be compressive. So go with axial, and then axial stress. Let's call this just y equals P over A, where P is 50 kilonewtons. Then the area equals pi over 4 times diameter squared. So area equals 1.96 times 10 to the negative third meters squared. Plug that in. And then we can solve. And we get negative 25.5 megapascals because it is compressive. Next, we can look at the moment about the x-axis, because if you really think about it, moment about the x-axis is going to create compression on the side that H is on, and then tension on the side opposite of H. So that's why that would create a normal stress. So this is due to bending. I'll just call this sigma x. And that is equal to the moment times c over I, with c being the distance from the central axis to the point of interest, and then I is the moment of inertia. So I for a solid cylinder is equal to pi over 4 times the radius, 0.025 meters to the fourth. So I equals 3.068 times 10 to the -7th meters to the 4th. All right, cool. And all right, I just got to plug everything in. Moment. 22.5 kilonewtons per meter times 0.025 meters over 3.068 times 10 to the -7th meters to the 4th. So this gives us sigma mx equals -2,623 megapascals. Once again, because it's compressive. So these are the only two loads that we have to worry about, because if we look at the 17 kilonewton load, the moment it's producing is like the plane is parallel to the plane that H is on. And since H is on the neutral axis of where it's taking the moment about, I don't know if that's the best way I could explain it. Let me draw a picture. This is H right here. This is the y-axis. Since the moment would be going like this, there is no normal stress created. If it was out here, it would be, because it would be compressed, and this would be tension. But since it's in the middle, it's on the neutral axis, we don't have to worry about that. So that's nice. I need to erase that. All right. So those are the only two normal stresses that we have to worry about. That means the normal stress at H is going to be sigma y plus sigma x, or -25.5 megapascals minus 2,623 megapascals, which gives us 2,349. That's not right. Hold on. $1,649.3 megapascals. Okay. Now let's worry about the shear stress created, which would be created by just this torsion right here. So see how the 9 kilonewtons is kind of twisting this cylinder with the moment that it creates? That's going to create shear stress at H. So stress due to torsion. That is given to us with, let's call this, oh no, tau yx equals torque times C over J. C once again being the distance from the neutral axis to the point of interest, and J being the axial moment of inertia. So J is equal to pi over 2 times the radius. Plug that in, get 6.13 times 10 to the negative 7th meters to the 4th. Now we can plug this in. Torque is 22.5 kilonewtons per meter. This just comes from the moment that we found about the y-axis. Same radius, 0.025 meters over J, which we just found. J is 6.13 times 10 to the negative 7th. Meters to the 4th. All right. Plug that in. Tau Ix equals 917.6 megapascals. All right. So that's going to be our only shear stress that we have to worry about. And since we have our normal stress at H already, we can now use Moore's circle to find the principal stresses and therefore the maximum stress. The equation that we use to find the principal stresses using Moore's circle, sigma 1 comma sigma 2 sigma x plus sigma y over 2 plus or minus square root sigma x minus sigma y over 2 squared plus the shear stress squared. So we only have normal stress in one direction, so one of these can go away. If we did have stress coming at it from, say, the sides of the cylinder, then we wouldn't be able to put that away, but that's not the case in this problem. So we have negative 2,649 All right. Now I just need to plug that into our calculator. Sigma 1, or sorry, sigma 1 equals negative 2,935.8 megapascals. Sigma 2 equals 286.8 megapascals. And if you remember Moore's circle, these are on the opposing sides of the circle, and therefore the radius is going to be the maximum shear stress. So we find that by taking the average of these, which is just sigma 1 minus sigma 2 divided by 2, tau max equals 1,611.3 megapascals. And this right here is our final answer. All right. This is all my work if you want to look at it again. It kind of got bigger the more I got along because I kept zooming out but writing at the same size. It's kind of funny. All right, but that's it. I'm going to sign off. Thank you for the semester.